Or if you are accurate enough to draw the graphs on your own, that's fine too, but you'll probably want some grid lines to be able to draw the graphs. So, first thing here says,
Carter, yeah, my brother.
hurry up.
Carter Belfort.
Suppose we know the following information about a function f of x. The domain of f is... Now, this is some new notation for you. Some textbooks will use this notation. We usually use interval notation. But here's what it's saying. Okay? The domain of f is... And they give the d for domain. And they have the squiggly. And they have the x. And they just have a little vertical line. Okay? The domain of the function is all x values. So when you see that first x, that means all x values. And then the vertical line is basically saying when. Okay, so that's like saying when or where. Alright? So all x values when x is not equal to -1 or x is not equal to +1. Okay? So that's what they're telling you in this very first line. Is they're basically saying the domain is all real numbers except what?
-1 and 1.
-1 and 1.
So could you also say the domain is negative infinity, -1, -1, 1, 1, infinity?
That's how I've taught you guys to write it.
But this is another way.
Okay, this is just another way. Certain textbooks use certain ways to write their domains. Okay, especially when it can be a little confusing. Sometimes maybe it is just a little bit shorter. It's very similar. But this is basically what it's saying, is the domain would be all real numbers, all real x values, where x is not equal to 1 or x is not equal to -1. So in other words, everywhere except -1 and 1 is what it comes down to. Yes, Brett?
So those are parabolas, or do we not know?
No, what do you mean?
Well, I mean, if it encompasses everything but those two values, is there like...
We don't know.
I'm not asymptotes.
You meant asymptotes?
Yeah.
We don't know. It could be. Could very well be, but we got a lot more information to go with here to be able to draw that sketch. Doesn't have to be an asymptote. Could just be a hole.
Right.
We don't know. We just know that at 1 and at -1 there is not a defined value for the function. Okay. Then, so I gave you the domain. Now we kind of know that at 1 and -1 we're not going to have actual points. Then I gave you 4 coordinates here that are points on the function.
We just start by doing
So that would be a great start, is to just go ahead and plot those 4 points on your graph. Okay? So go ahead and plot those 4 points.
is positive on intervals and -1.
Now, you'll notice in parts C and D, they have given you intervals of what?
F prime,
Which would mean?
the derivative.
Which would mean? Which would mean?
Instantaneous something.
Which would mean?
What in the world are you looking for?
Yeah.
The slope.
Are you looking
That's good. Yeah, you're right.
for?
There's more though.
Okay, but what?
Rise over.
If it's going up or down from one point?
So
Concavity intervals and
Extrema.
when it's going up, what's it doing?
increasing, decreasing.
Increasing, decreasing
Hey.
intervals. That's what I'm looking for. All right. Remember how on a test I look for increasing, decreasing intervals? And the second derivative, those are called what type of intervals? Concavity intervals. Okay? So in parts C and D, they're telling you when the function is increasing or decreasing. they're also telling you when the function is concave up or concave down. That's what parts C and D are telling you. Personally, I jumped down, when I did this problem, I jumped down to E and kind of take care of those things first before messing with those.
That makes sense.
Okay? Because I'd like to know if there are any asymptotes, because if I know if there's asymptotes, that will help me a little bit to draw the curve before I start making them going up or going down, or concave up or concave down. So I'm actually going to jump to E. This is my personal preference. I just think it's easier, because otherwise I don't really know. Okay? So let's look at this one right here, the first one on E. The limit of the function as x approaches -1 from the left
Oh.
is 2. But keep in mind now, is this function defined at -1?
No.
No.
No. But is it okay for it to have a limit?
Yes.
Yes.
So what does that mean then?
It's a whole.
It's a whole. So at -1,
Well,
at -1 it's going to be approaching 2 from the left. I don't know what this graph's going to do. I haven't read any further, but I know that as I approach -1 from the left side, my graph's going to get really close to 2. So I put a little open circle right there. Does that make sense?
Yeah.
except since it's going from the left, couldn't it theoretically also be approaching from the right to a different spot?
Yeah.
It is.
Yeah, it is.
We haven't gotten there yet.
Hole there.
I'm just, from this first statement, that's all I can do right now.
Okay.
Right? Okay? Now, the next one says the limit of the function as x approaches -1 from the right is +1.
Uh-oh.
Oh, yeah.
That's
So to
wrong.
me, I'd put another open circle right here and know that the graph is approaching a +1 from the right.
Yeah.
Now, more than likely, it's probably going to end up going through that point. They're so close, but I'm not going to connect them or anything yet. Okay? I'm just kind of drawing just enough to know that, hey, I know I got to get really close to that value as I come to, as I get really close to -1 coming from the right. Okay? So I've taken care of this one, I've taken care of this one. The limit of the function as x approaches a +1 from the left is -infinity.
Uh-oh.
Oh,
That's a horizontal aspect.
Probably going to have an asymptote at 1 then, right?
We will indeed.
Wait, no, that's not.
Because the limit of the function as x approaches 1 from the left, so in other words, as we get really close to that vertical line at 1 from the left, it's going to be headed towards -infinity. At this point, just by purely randomly guessing, but I'm not quite sure, I haven't checked these things, just because I know what functions tend to look like, I might draw something like this right now.
You don't know
That's what I drew. Well,
Okay.
sort
that. What
of.
if it goes right up and then right back down?
Well, yep, and then I'll have to use an eraser.
Yeah. Yeah, you would.
So for right
Let's
now.
use-
So I would not use my pen, alright?
Don't make mistakes. Do not make mistakes.
And then from the
Okay.
other direction, it's going to infinity.
So I did that one.
Wait, John, you're thinking.
The limit of the function as x approaches 1 from the right is positive infinity. So I'd be willing to bet the graph's probably doing this.
Wait, somewhere.
The limit of the function as x approaches 1 from the right
Is positive.
is positive infinity. So as I get close to 1 coming from the right, the graph is going towards positive infinity. So I'm going to guess that it's probably going to look something like this over on this side.
I was like, we should do this, or you're just
I haven't.
really educated guesses.
These are educated guesses. I don't have my answer key with me anymore, and I don't physically remember exactly what it looks like. I'm just telling you, this would be my thought process as I'm going through the problem for the first time.
We got
Okay.
some horizontal asymptotes.
The limit of the function as x approaches -infinity is 0. So John says there are going to be
Johnny Cash.
horizontal
horizontal asymptotes. So as the graph goes way to the left,
It's gonna approach 0.
it's going to approach 0. Okay? So, being that the graph had to get close to this from the left, maybe I'll draw something like this. Okay? And then as we approach positive infinity, the graph approaches -1. So if here's -1 right here,
It'll approach it.
okay,
So that,
I might even just draw the arrow right out there because I really don't know what's going to go on for sure in between there. And I could have done that over here too if I wanted to, alright? I could have maybe just put a little arrow right here knowing that I'm going to get really close to 0 and not connected them, okay? I don't know, I got to go back and check positive and, or increasing and decreasing intervals and concavity intervals yet too, okay? But I do know that as I approach here, it's going to be approaching -1. Now yeah, because who knows, maybe it comes up and then back down. I don't know, I got to figure out a few more things here.
Alright, direct. So now would we go back and be like for the f prime?
I'm going to work on increasing, decreasing then, yeah. Okay? Alright, it says that f prime is positive on the intervals -infinity to -1. So that tells me the graph, as I go from -infinity to -1, my graph better have a positive slope. My graph better be increasing. Well, we know that as we went way this way, the limit of the function was 0. So essentially there's a horizontal asymptote at 0. But as we're moving this way towards -1, the graph has to be increasing. So actually what we had probably makes some sense. Doing something like that. Okay? The graph, the slope of the curve, is always increasing as we approach -1. So I've taken care of this one right here.
So then would we go over to our point that's at 4?
Yep. It's also increasing from 4 to positive infinity. Well, here was the coordinate at 4, and if it's always has to be increasing from here to the right, and we know the limit of it as we go way to the right is -1, okay? It always has to be getting larger, so maybe something like this.
Mm-hmm.
how does that in between the goals that getting larger?
The slope is getting larger. Because
Oh, yeah, okay, okay.
I didn't ever have the graph dip down at all. I kept it either, well, I wanted to have it slowly increasing there a little bit. Okay? It's decreasing from -1 to 1. Well,
That works.
that works, but we already drew there, so good educated guess, I guess, there. Okay? And then it's also decreasing from 1 to 4.
So could we just connect?
So that tells me then that at 4, if it was decreasing as we got close to 4 and then increasing after that, what would that tell me occurs at 4?
Minimum,
A minimum.
which we can check. Right now, that does show that it is.
Okay? Alright, so I got those.
Okay.
And now let's check the concavity intervals. If f double prime is positive, that means the graph should be what? Concave up or down?
Oh,
Concave up when the second derivative is positive. So from -infinity to -1, the graph should be concave up.
Yes.
Would you agree that this, a graph that looks something like this, is concave up?
Yes.
Okay, so I'd say we're okay there. From 1 to 5, concave up.
yeah.
Yes.
So this is kind of like a parabola right there until we get to 5. So then if it's concave down after that, what's this point called?
Inflection point.
Inflection point, good job. Okay, so the graph is going to be concave up until we get right here, and at that point it switches to concave down. So we actually kind of took care of both of those right there. And then is it also concave down from -1 to 1?
Yes.
Yes.
That would be from here to here. Looks like we got kind of half of an upside down parabola. So I'd say we can check that mark off.
Wait, guys.
And we have drawn a rough sketch of this function, just given all of this information right here. Okay? So, it makes you think about a lot of the different things we've done so far in calculus, and then being able to draw kind of a rough sketch to represent whatever this curve, I can't really necessarily call it a function. It is a function, except it's not defined at negative 1 and 1.
Right.
Okay? Alright? So,
It could be a
that's
few.
kind of one of the things that you'll be asked to do. I left one more for you, number 2, for practice. Alright, but I wanted to go through the first one with you. Turn your sheet over.
Domain of F. So is this
Instead
like
of
the
giving-
steps?
Instead of giving you all the characteristics of a particular function, I might just give you a function rule. Okay? I might just give you a function rule or a function itself. And I think we can kind of work through one a little bit as we do this. Okay?
Oh.
Okay? This is kind of a checklist of all the things that will be very helpful for you when it comes to sketching the graph. When you do get some of these to practice, I would kind of go through these items on each one of the problems to help you draw the graph, to help you do the first and second derivative tests, and so on. Okay? Domain. That's sometimes one that we skip, alright? Because you're so used to getting fairly easy functions. They're polynomials, like the one I gave you for an example
This is
right
not
now.
Negative infinity
Okay.
to infinity.
Mm-hmm. But there are times when a function does not have a domain of all real numbers. And it's really kind of wise to know that before you start doing a lot of things with it. Because like we've talked about before, with the critical points, knowing when things are defined or not defined, that can sometimes impact what we get for our increasing, decreasing intervals, or maximums or minimums, okay? So it is good to think about what values are actually in the domain of F. Now, the example we're going to do here first, obviously my domain would be what?
Negative infinity, infinity.
Negative infinity to positive infinity, all real numbers, okay? But the domain of F, here's what you really need to think, okay? Are there any x values not in the domain? Okay? And if so, make sure you're aware of that, okay? So when I ask you to find the domain of F, really what I'm asking you to think about, are there any x values that would not be in the domain and therefore impact what the graph of this function would look
So in
like?
other words, see if you could possibly get an I or a 0 on the denominator.
Very good, yes.
Are those the only
Anything
two?
undefined, correct.
Are
Yep.
those the only two
Okay.
that we have at this
Um,
point?
Even roots of negative numbers, denominators of 0
So
covers it.
Yeah.
Yes. Mm-hmm.
imaginary numbers are okay.
Yep. Yep. Okay. Or I guess if it's a piecewise function and it's just simply not defined for a particular x value, maybe Luke too. But, okay. All right. So do think of that when you go to graph these. All right. X-intercepts. How do you find x-intercepts? You plug in 0 for y, solve for x. Okay. Plug in 0 for y,
Oh, that's why.
solve
Huh.
for x.
So 0 and 6.
Right?
Okay.
Those are potentially some easy coordinates for you to find. Okay, they're not always easy. Y-intercepts usually are very easy. Okay, how do you find y-intercepts? Yep. Plug in 0 for x. Solve for y. Okay, those are pretty simple there. Vertical asymptotes. How do you know when something has a vertical asymptote?
Find the limit find the limit of infinity or negative infinity as
Whatever makes the bottom equal 0.
What you said was correct. That is true. Visually, most people are probably going to think what he said. Whatever makes the denominator 0. Okay? Whatever makes only the denominator 0. Right? Because what if it makes both numerator and denominator 0?
It's a whole.
It's just a hole in the graph. So, vertical asymptotes. See if there are any x values that make only the denominator equal to 0, and therefore then you will know you have a vertical asymptote. Which then, if you find the limit of the function as x approaches that from the right or the left, you'll find whether it goes to positive infinity or negative infinity.
What is it called, the parts where they don't exist because of imaginary numbers, like the square root of x?
It's just,
doesn't exist or doesn't have a name.
yeah, no real solutions or real values.
And how would you mark that on a graph?
You
You just
put
wouldn't
in
draw anything
points.
over there. That's why
Like,
you're...
think of the square root of x graph. There's nothing to the left of 0, 0. It's
Oh.
all just the line to the right. Because anything to the left, x would have to be negative. The square root of a negative number is going to be I something.
I was thinking if you
And
had
I is
something in the middle of your
imaginary.
function, but that doesn't make sense, because,
No.
yeah.
Okay. So vertical asymptotes, see when the denominator equals 0. Obviously, no denominator, no vertical asymptotes, right? Horizontal asymptotes, how do you check for those?
Yeah, I'd use the limit thing.
This one I definitely would use the limit, okay? Find the limit of the function as x approaches both positive and negative infinity, okay? That's how you'll find all of your horizontal asymptotes.
As long as it's not a piecewise.
Okay. What do you mean?
Well, like, if it's a piecewise, then theoretically, couldn't you have a limit in the middle? Or, horizontal in the middle. Or would it not count as that? Because it, oh, I guess it does stop at a certain point,
Yeah.
so it's still.
Horizontal asymptotes are always at the far ends of the graph.
Okay.
Because essentially, you can't say they're really over the entire graph because it might cross that horizontal asymptote more in the middle. Officially by name, horizontal asymptotes always occur at the very left and right end.
Okay, that makes sense.
Okay? So
'Cause I
that's
guess
how
it
you
would
found
have to
horizontal
stop.
asymptotes. As x gets really big, in this one, so does y. So therefore, it doesn't approach a particular value, okay? If it does approach a particular L value or whatever, then that would be your horizontal asymptote. But as x gets really big, y is going to get really big. As x gets really small or really far negative,
It's gonna be really.
it's also going to go really far negative. So in this case, again, no horizontal asymptotes. Probably not going to have any horizontal asymptotes either, unless you have a rational function. Okay. How do you check for intervals of increasing and decreasing?
Same as usual, derive it and.
So 0
Derive,
and 4.
so first derivative test, basically. Okay.
0 and 4.
So first derivative test. I'm just kind of going through how we do all this right now.
Set it equals to 0, right?
Well, you set it equal to 0, set the first derivative equal to 0 to find your critical points. And then you remember how you test numbers between all those critical points to see whether it's increasing or decreasing?
Sure, right.
Yeah. Is that right? Okay. Relative extrema?
0 and 4.
What? In general. See how I've kind of been going through just in general what we do? How do we find relative extrema?
Correct.
Local maxes, local mins.
See if it's increasing and decreasing from like the critical points on, is it the critical points?
Yep,
that we use?
yep, perfect.
Yep,
Yep.
that was real cute.
Using the critical points and using our first derivative test to determine if the graph was increasing and then decreasing, therefore we'd have a max. If it was decreasing then increasing, therefore we'd have a min. Okay? So you're kind of using critical points and first derivative test again. Okay? me to go back up here to make it a little more clear too. You're using the first derivative and you're checking to see if its value is positive or negative. If it's positive, it's increasing. If it's negative, it's decreasing. And very similar down here,
Second derivative.
these are using the second derivative. Okay? So again, second derivative, looking for positive or negative.
Okay, so now we find the inflection point.
And then here, how do you find your inflection points?
Those are those.
The original.
That's when the second derivative equals what?
Zero.
Equals 0. When you set your second derivative equal to 0. Or if it's undefined, right?
Yeah.
I can maybe put that back up here for relative extrema as well. When the first derivative equals 0 or is undefined. Okay.
What would that mean? So, quick thing, and I know this is kind of a silly question. Which one's concave up and which one's concave down?
Up positive. Second derivative is
Okay.
positive.
So it's simple, positive
Mhm.
up, negative down.
Yep.
Yes.
And then it's